Hey guys, welcome back. Today we'll be looking at asymmetric encryption. We are still on the introduction to cryptography room on TryAcme, which is a free room. So let's begin. We know that symmetric encryption requires the users to find a secure channel to exchange keys. This is because the key that is used to encrypt is also the key that will be used to decrypt. By a secure channel, we are mainly concerned with confidentiality and integrity. In other words, we need a channel where no third party can eavesdrop and read the traffic. Moreover, no one can change the sent messages and data. Asymmetric encryption makes it possible to exchange encrypted messages without a secure channel. We just need a reliable channel. And by reliable channel, we mean that we are mainly concerned with the channel's integrity and not the confidentiality. I'm sure by now you know the difference between integrity, confidentiality, availability, and authenticity, right? So when using an asymmetric encryption algorithm, we generate a key pair, a public key and a private key. The public key is shared with the world, or more specifically, with the people who want to communicate with us securely. Now, the private key must be saved securely and we must never let anyone access it. Moreover, it is not feasible to derive the private key despite the knowledge of the public key. So for asymmetric encryption, a different key is used to encrypt and a different key is used to decrypt. So the public key is public, like everyone that wants to communicate with you specifically, we know the public key. While the private key is just you that is going to know that it is saved securely. And again, you can't derive the private key from the public key. In case you're wondering, what if one can kind of like be able to get the private key from the public key? It's not feasible. So how does this key pair work? If a message is encrypted with one key, it can be decrypted with the other. In other words, if Alice encrypts a message using Bob's public key, it can be decrypted only using Bob's private key. And reversely, if Bob encrypts a message using his private key, it can only be decrypted using Bob's public key. I hope you are getting it. So we move on to confidentiality. We can use asymmetric encryption to achieve confidentiality by encrypting the messages using the recipient's public key. In the following two figures, we can see that Alice wants to ensure confidentiality in her communication with Bob. She encrypts the message using Bob's public key. Now, Bob will decrypt the message using his own private key. So, Bob's public key is expected to be published on a public database or on his website, for instance. So, this is plain text by Alice being encrypted using Bob's public key, which is converted into a ciphertext. Bob is going to receive the ciphertext and decrypt it to plain text using his own private key. Now, when Bob wants to reply to Alice, he is going to encrypt that message with Alice's public key, not his own private key. So he's going to encrypt it with Alice's public key so that Alice can decrypt it with her own private key. So that's just how it works. If Alice is going to send to Bob, she's going to encrypt with Bob's public key so that Bob can decrypt with his own private key. And if Bob is going to send it to Alice, Bob is going to encrypt with Alice's public key so that Alice can decrypt it with her private key. So just Bob and Alice are in the communication channel. In other words, it becomes easy to communicate with Alice and Bob while ensuring the confidentiality of the messages. The only requirement is that all parties have their public keys available for interested senders. Note, in practice, symmetric encryption algorithms allow faster operations than asymmetric encryption. Therefore, we'll cover later how we can use the best of both worlds: integrity, authenticity, and non-repudiation. Beyond confidentiality, asymmetric encryption can solve integrity, authenticity, and non-repudiation. Now, let's say that Bob wants to make a statement and wants everyone to be able to confirm that this statement indeed came from him. Bob needs to encrypt the message using his private key. The recipient can decrypt it using Bob's public key. If the message decrypts successfully with Bob's public key, it means that the message was encrypted using Bob's private key. In practice, you would encrypt a hash of the original message, which we'll elaborate on later. So now, if Bob wants to make sure that everybody that receives the message can confirm that it came from him, he's going to encrypt it with his private key so that when they use his public key, they are going to be able to read it and confirm that truly it is from him if it gets decrypted successfully. So being decrypted successfully using Bob's public key, will lead to a few interesting conclusions. First, the message was not altered across the way, that is the communication channel, and this proves that the message is having integrity. Second, knowing that no one has access to Bob's private key, we can be sure that this message did indeed come from Bob. This proves the message authenticity. Finally, because no one other than Bob has access to Bob's private key, Bob cannot deny sending this message, which establishes the non-repudiation claim. We have seen how asymmetric encryption can help establish confidentiality, integrity, authenticity, and non-repudiation. In real-life scenarios, asymmetric encryption can be relatively slow to encrypt large files and vast amounts of data. In another task, we will see how we can use asymmetric encryption in conjunction with symmetric encryption to achieve these security objectives relatively faster. We are moving on to RSA. RSA got its name from its investors, Rivest, Shamir, and Edelman, and it works as follows. 4 steps. Please pay attention. 1. We are going to choose 2 random prime numbers, P and Q, and you are going to calculate n equals to P and Q. If you are wondering what prime numbers are, you are going to come here prime numbers, meaning. So we can say that. Oh, it's taking long. Okay, I'll wait for that to load. So we are going to choose 2 integers, E and D, integers. So this is how you learn. Don't assume you know already. Sometimes it's just good to be sure that what you think you know is actually what it is. My network is slow today. What's happening? Excuse me. So we are going to choose 2 integers, E and D, such that E times D is equal to be 1 modular n, and where modular n equals to n minus P minus Q plus 1. This step will let us generate the public key n, E and the private key n, D. Now the sender can encrypt a value x by calculating y equals to x raised to power e modulo n. And the recipient can decrypt y by calculating x equals to y raised to power d modulo n. So this step explains why we put a restriction on the choice of E and D, 2 integers, don't forget. Now don't worry if the above mathematical equations look too complicated. You don't need mathematics to be able to use RSA, as it is readily available via programs and programming libraries. I'm wondering why this is not working. Okay, I think we'll be needing our attack box. So I'm going to start the attack box now. By the time we get to the task part, it should have loaded. And I'm going to exit split view. So it loads in the background. So now, RSA security relies on factorization being a hard problem. It is easy to multiply P by Q. However, it is time consuming to find P and Q given N. Moreover, for this to be secure, P and Q should be pretty large numbers. For example, each being 1024 bits, and that's a number with more than 300 digits. So it is important to know that RSA relies on secure random number generation, as with other asymmetric encryption algorithms. If an adversary can guess P and Q, the whole system will be considered insecure. Now let's consider the following practical example. 1. Bob chooses two prime numbers, P, which is equals to 157, and Q, which is equals to 199. He calculates N, which is equals to 31243. Don't forget, N equals to P times Q. Yeah. I'm amazed. What is wrong? Damn it. Now, with the modulo N, which is equals to N minus P minus Q plus 1, N 31243 minus 157 minus 199 plus 1, which is equals to 30888. Bob selects E. Sorry. So we can see that Bob selects E equals to 163 randomly, and he also chooses D equals to 379, where E times D will give us 61777. So 6177 modulo 3088 equals to 1. The public key is this, and the private key is this. Now, let's say that the value to encrypt is x equals to 13. Then Alice would calculate and send y equals to x raised to power e modulo n, which is equals to 13 raised to power 163 modulo 31243, which is equals to 16342. Bob will decrypt the received value by calculating x equals to y raised to power d modulo n, which is equals to 16341 raised to power 379 modulo 31243, which is equals to 13. Now, this example is just to understand the mathematics behind it better using real numbers. To see real values for P and Q, let's create a real key pair using a tool such as openssl. It's not that the network is slow. I hope my attack boss shut out that. Okay, we're going to open a terminal. So now we are going to generate keys using openssl. Don't forget that openssl is a tool that can be used for both symmetric and asymmetric encryption. Now, the first command we are throwing at it, just come to your terminal, do openssl generate RSA. Don't forget that's the name of the algorithm we are using. Out private key dot pem 2048. Enter. Okay. Now to open SSL RSA in private key dot pem dash PUBOUT out. What's PUBOUT out? Public key. Can actually copy and paste this, but I just like to type it out myself. So we have the output writing RSA key. Then we do cut public key dot pin. So this is our public key. We have it. Then we are going to do. So we are going to explain this when I'm done. Open SSL RSA in private key dot pem dash text no out. Okay, exponent coefficient. So we executed 3 commands, right? The first command with openssl, that's the tool we are using. We use gen RSA, which is generate RSA private key. So we are trying to generate RSA private key. The command out specified that the resulting private key is saved as private key.pem. So what this means is that if I want to save it as something else, I can just write Ben's private key.pem, right? So we are right. The 2048 is to specify that we want a key size of 2048 bits. Now that has been generated. For the second command that we ran, we have openssl. Don't forget that's the 2. Then the RSA to tell it that we are using the RSA algorithm. The initial one is what? Generate RSA. That's why we have gen RSA out. We are generating a private key into this file called private key.pem. Now, the second command, we are trying to use this RSA. So we are telling the openssl, we are using RSA algorithm with the RSA option. Then we wanted to get the public key using pop out. So we told it that the in private, we created a file called in private key.pem for the private key in the first command. We are telling it that the input we want it to use this private key.pem as the private key. And we want it to save the output into public key.pem. So this pop out is to generate the public key. I want it to be generated into the public key.pem. First step, we generate private key. Now, to generate the public key in the second step, we are going to make reference to the private key. So you tell it openssl, we tell it is RSA algorithm, we tell it the private key, and we tell it that we want it to generate a public key from that private key. And we tell him the name of the file we want the public key in. That's just it. So the third step, we did openss. Did I do this third step? Yeah. Okay. So this one, we just want to see the content of the public key. That's why we did the cat option, the cat command rather. On the third command, we did openssl, that's the name of the tool. RSA, we tell it that's the algorithm we have. Then we have in private key.pem. We want it to look into the private key, and we want to see the real variables that was used. That was why we did the -test -no out, so that we can have all the values of the variables that we explained earlier. So these are the variables. Can you see them? The public exponent, the private exponent, the prime 1, the prime 2, the exponent 1, exponent 2, the coefficient. Everything has been output for us. So if we already have the recipient's public key, we can encrypt it with the following command. And if we have the private key, we can decrypt. Now, so now let's say we have, this is the key. Don't forget, we generated a public key and generated a private key. Now we are trying to encrypt a message using the recipient's public key. That's the key we generated. Do not forget. So Control L to clear my terminal. So I'm going to come here, openssl, PKEYU, T, that one or L? No, it's one. Okay, good. Then we tell you we want to encrypt in the name of the text, the file rather. So we can decide to say plain text dot text. We can decide to say my book dot text, whatever we want to call it. So let's follow the instruction. Plain text dot text. You can even name it baby dot text, whatever you like. Then we are going to want to convert to the cipher text. So do we have a plain text dot text? I don't think we have that file, but anyways, let's go. Should have created a plain text dot text. So we want it to output it into cipher text. That's the name of our output. Using this key in key, public key. Don't forget we created that public key initially. .pem pub in type help. Okay. That means something. I didn't create a file called plain text, but let's see if that's going to work still. Now you can see that it says that can't open plain text dot text for reading, no such file or directory. We haven't created that file. That's why I could not find it. I was just following that description. So in case you want to encrypt the file, you need to have created a file you need to be encrypted, or whatever the content of your file to be encrypted. You need to have created it before you use the command. So on the attack box, you can find the directory for this task located at. So we are going to cd. Let me put my working. Let's see what we have first. Then the root. So cd rooms. Roots. Cryptography. Don't forget these. They are case sensitive. So if you are seeing capital letter, it is capital letter it showed. Task 03. Enter. So we are going to list the contents of this directory. So we can see that we have the keys we are supposed to use. So Bob has received the file ciphertext underscore message sent to him from Alice. You can find the key you need in the same folder that has Alice's public key, right? What is the first word of the original plain text? So they want us to decrypt ciphertext message using Alice's public key, since Alice was the one that sent it to Bob. So now what we are going to do, we are going to use the decryption command. Don't forget, we have openssl, pkeyutl, good. Then we want to decrypt, so decrypt, fine, in our ciphertext. That is what ciphertext underscore message. So we type ciphertext underscore message. Good. Then we are going to tell it the key. In key. Then we tell you the private key. The private key we have is, okay, Alice's was the one that sent it to Bob. So Alice must have encrypted it using our own. Okay, okay, let me come again. Alice must have encrypted it using Bob's public key. So Bob needs to undo it using his own private key. So what's Bob's private key? We are going to do private key dash Bob dot pem. Then we need to tell it where we need him to, where we need to tell the command where we want the decrypted message, that is the plain text, to be. So we do out, we want it to output it into, let's say, plain text message. Plain underscore, plain text underscore message dot txt. Enter. So let's see if it has done that. Earlier, we should have a plain text underscore message. Okay. So we are going to view the content of that. Good. Perfect. So what is the first word of the original plain text? That's perception. Perception. Now let me explain this once again. Bob has received the file ciphertext message sent to him from Alice. You can find the key you need in the same folder. What is the first word of the original plain text? If Alice is sending a message to Bob and she's sending an encrypted message, that means she's going to use Bob's public key to encrypt the message. If Bob needs to decrypt the message, he's going to use his own private key to decrypt it. So what we just did was to run the commands. First of all, we navigated into the folder that had all the files in it. Then we run the command using openssl pkuytl decrypt. That means the file wants to decrypt, that's the ciphertext message in, right? The private key we'll be using is Bob's private key, so in key, then Bob's private key. Then we need it to bring out the output into a different file. That's why we're using the out command. Then we give the name of the file to it. It is going to create it simultaneously that way. Plain text underscore message.txt. I hope that is clear. Good. We're moving to the next task. Now, take a look at Bob's private RSA key. What is the last byte of P? Bob's private RSA key is private key. So we're going to cut private Bob. Oh, sorry, private key Bob. Private key Bob dot m. Yeah, so we have Bob's private key. What's the question? What is the last byte of P? What do you mean by that? The end of private key. Hints. Let's look at the hints. Prime is prime 1. The answer should be 2 hexadecimal digits. 2 hexadecimal digits. Is it OG? No, your answer is incorrect. We have the contents of the private key. Okay, I think we're shown how to open the content. Okay, yeah. So we want to check, we are curious, we want to check the variables actually. So this is what we are supposed to do. Not cat, open SSL. That just came to me. RSA. We're going to use the third command we used initially in. What's Bob's private key? Private key bob.pem, right? Then we see text no out. We are going to have everything here. And we are looking for the words. What is the last byte of P? So we are coming here to P prime 1. This is prime 1. And the last byte is E7. What we have here? E7. Right. I hope you understand. If we are trying to see the value of, this is an hexadecimal format. We are trying to see the value of the variables that were used, or constant variables really, for the private key, the command to run is different. If you just want to see the key, you are going to use the cat command. Control L. Let's clear the screen. Now, take a look at Bob's private RSA key. What is the last byte of Q? Q should be quotient. Oh, prime 2. Okay, good. So we just need to scroll back and look for prime 2. Yeah, and that's 27. Good. So with this, we have come to the end of asymmetric encryption. We've been able to see how to encrypt all the RSA. Okay, we have come to the end of RSA asymmetric encryption. We're able to see what the technology behind look like, the prime number, the variables, the X, the Y, the E, and all that. We've been able to generate a private key using openssl. We've been able to generate a public key using openssl. We've been able to print out the values of the variables in the public key, or if rather in the private key using openssl. We've been able to decrypt a message using openssl. It's okay if you don't get it now. You can actually go over it till you figure out and understand how it works. Thank you very much. In the next class, we'll be looking at the Diffie-Hellman key exchange, which is also a form of asymmetric encryption algorithm. Bye for now.